Yeah, this thing just worked 10 seconds ago, so that's the usual. But no problem, I can just use the spacebar. Thanks. Oh, yeah, it works. Cool. Hey, everyone. My name is Miłosz. I'm the co-founder of Fields Labs. So together with Robert, who is speaking after me, we run a tech blog at 3.Tech. And we a couple other things, like we maintain the WaterMe library, and when we also run online trainings recently. So if you want to learn anything about us, just visit the page. Yeah, we live in Krakow in Poland, so thanks for inviting us. It's actually my first time in Prague. It's really, really nice so far. So yeah, thanks for coming. And this talk is about CQRS. So it would make sense to start with some kind of a definition, right? First, the question for you, can you raise your hand if you know what CQRS means or what it is? Right, and if you have used CQRS in your project successfully or not? Cool. So the good news is, whether you know what it is or not, it doesn't matter, because I'm not going to tell you, at least not right away. And the reason is, I think definitions are not that useful when you want to learn new things, right? Because especially about programming techniques or patterns, definitions often tell you what something is, but not exactly why you need to use it, right? Or they tell you how to apply some technique, how to structure your code, but they skip the part when it makes sense to do it and when it's better to avoid it. And then we sometimes end up, hearing from people like, how do I use all those solid CQRS DDD patterns in my Go project? And if you look online, it often ends up with discussions like, someone asks this question and then someone comes in and says, like, stop doing Java in Go. This is not Java. We shouldn't do this OOP stuff here. Which, I'm not here to tell who is right in this discussion. My point is, it's rather pointless, because very often one person thinking about DDD means something completely different than another person, because it depends on how they use it in a project. Maybe someone used it in a different way. So yeah, it doesn't really make sense to discuss this. And what I think it makes more sense is experience, right? So you try some things, you experiment in your project, you see some things work well, so you keep doing them. You see some things fail, so you stop doing them. And it gives you this pattern recognition in your brain. So the next time you see some issue, you remember, oh yeah, I know, this is how I fix this. This is the pattern I use. And I'm sure you have your own patterns like this that you know. I really like this fact, because it helps me to focus on the high-level concepts when programming. So when creating a new application, I don't need to dive deep into the implementation details. I can just come back to something that worked for me in a different project. But the hard part about it is, if you want to explain to someone else why this works, you need to come up with some definition, right? And the problem is, the other person doesn't have all this context that you have because of all the experiments you did. So what I want to do today is tell you about 3 projects from my experience where CQRS turned out to be useful, or at least some parts of it. And what they have in common as well is that I didn't start them thinking, oh yeah, this is where I use CQRS. But instead, looking back, I realized, oh yeah, this actually was CQRS in action. I just didn't realize it at the time. And just in case you're afraid that CQRS sounds like something enterprise Java, this all happened in startups using Go as the primary backend language. So it was quite a fresh tech stack. So I work on a project management application. You can think like Jira, but more modern and simpler. And we used a quite complex architectural pattern there. You might recognize this one. So we had a Go backend server that was connected to a database. In our case, it was MongoDB, because back then Mongo was web scale, and we also wanted to be web scale, but it doesn't really matter. And there was a front-end client talking with the backend with REST API. And we had a couple of entities, as you can imagine, in any web application, right? The primary one was task, like a Jira task or issue, right? And it had a couple of fields, and it also referenced other entities by ID. And those entities lived in their own collections, which is something like a table in MongoDB, right? And yeah, they were connected using the ID. So I think so far there is nothing controversial. And we had this structures for entities in the code. So for example, for the task, we had a struct with all the fields, and we used the struct tags for marshalling and unmarshalling. Right, so JSON for the REST API, as usual. And for Mongo, we used Bison. If you don't know Bison, it is binary JSON. It's basically what Mongo uses for marshalling. So we had this struct in the middle that we used to transfer between the JSON API and the Bison database. And yeah, we had this /tasks REST API, the tasks collection, and the task structure. So it seemed like clean code, whatever this means, because if you thought about task, knew exactly where to look for it, where to find it in the code, in the API, in the database. It was nice and clean, deduplicated. But then one day, our front-end team came to us and said something like, "Your API sucks." So our first instinct was to blame JavaScript. Right? This must be some library they use that is not compatible with our API, which is modern and clean. Well, it turned out the issue was the IDs we were returning in the response. So this is how that example task response looked like, right? So it's basically the struct marshaled into JSON. So it turns out our website didn't look like this. It rather looked like this. So the front-end team was annoyed because for every entity ID we returned, they had to call a separate API with the ID, fetch the details, and then do some magic on the front end to wire it all into one view. So what they would prefer instead is to have a response like this. So instead of the IDs of other entities, we should embed the full data of the status, of the assignee, of the reporter. So then they can just fetch the single endpoint and map it onto HTML and be done with it. So being good colleagues, we started thinking what we can do about it. So I guess nowadays you could think about GraphQL, but back then it wasn't that popular. But anyway, it seemed like an overkill. And also having some separate backend for front-end API maybe could make sense, but we thought about it, and running a separate server just to map some entities seemed too much. But thankfully we're programmers, right? So we looked for something smarter, something we could just write once and then work everywhere. I don't know, that's Java, sorry. But and we found something like this. So I don't know if you realize, but if you use the reflect package in Go, you can implement your own custom struct tags. And we decided to do it, right? So to our task structure, which used JSON and Bison, we added an entity tag that would describe what the ID refers to, right? What one entity is underneath this ID. And then we had a library that during marshalling of the task or any other entity would call the database, check all the IDs, and then remove the ID from the response and replace it with the full response of the entity. So basically what the front-end team wanted. And yeah, at first we felt like geniuses because it was what we wanted to achieve, right? It was the smart idea, the smart solution. We just wrote this library once and then could use it everywhere. But if you started looking up the documentation for Reflect, you can stop right now because it wasn't that good idea after all. Because as you can imagine, if you use a static language like Go with strong types and start doing things with Reflect, it's probably time you should reconsider what you're doing, right? So the thing had a lot of magic in it, and it was hard to work with in the long term because any debugging and testing of it was a pain. So later we had a second chance because we started a new project from scratch with the same team, and we started thinking, how we can approach this in a different way. And we started with this very naive approach or trivial approach. So we just defined a separate struct for the task response that included the full models instead of IDs. And for the request, we stayed with the IDs because for the request, it was good enough. So we had two separate structs to define the task. And then we had even a third one to map it on the database. And we would just map between those three. And at first, it seemed like a ridiculous idea because of all the boilerplate, right? Like anytime you add a new field to the entity, you have to add it in 3 places, so it's duplicated. And what if you forget about it, or just skip it, right? Or map to the wrong field. But over time, it turned out it wasn't really an issue because it is some boilerplate, but it is something you write once and takes you 2 minutes, right? And if you make a mistake, it's very easy to catch it early in the test. And even now, it's even easier with like something like Copilot, right? You don't even need to think about it. So it turned out to not be that painful in the end, and it was for sure easier to manage than the magic reflect thing. So the first obvious lesson learned from here was that it was actually okay to have 2 models for the same entity, right? So we could have this task response with embedded models of related entities and a write model for the task. And it was fine, even though it seemed like a duplication. It was useful in the end. And the other thing I thought about much later, looking back at this project, was that how fast we were to assume the task entity should map to one task model. Like it was like very natural for us, automatic, right? We assumed we need this one source of truth for the task. And I think this might be because of the dry rule, which you heard mentioned in the first talk, right? So because we learn very early to not repeat ourselves, and it seems intuitive to avoid any kind of duplication. And sometimes it makes sense, but in this case, it turns out it was actually counterproductive. It made more sense to duplicate the data into places. So the second project, different team, different company, was a control panel or admin dashboard that we built for the operations team. So it was supposed to be a single place they can look up, what's going on in the platform, the overall health, look up users, and so on. And the architecture was, again, supposed to be quite simple. So we would have this control panel API that would contact a database and run some complex queries on top of it, return the results which the front-end client would show to the users. Well, the issue was the company went a bit too far with the microservices idea. And we didn't have one database, but instead something like this. We had 10 microservices, each with a chunk of the data we needed. So there was no way for us to just, query one source of truth for the data. We would need to contact all of them. So we started checking, what are the options we have. And one of the things the services exposed was RPC. Right, so in theory, we could just call the RPC endpoints, collect data we needed in memory, and then run some queries on top of it. But obviously, it would be super inefficient and probably not doable. And we would end up with lots of wiring because of it. So we ditched the idea. But the other thing the services exposed was events. So each time something meaningful happened within them, they would publish this as a fact on a message queue. And actually, the events contained what the data we needed for querying, so it could work. But we needed a way to make the control panel API search for the events, which wasn't that obvious. So we started thinking, can we just build a database out of those messages? And this is the way we took. So we had like an asynchronous process in the service that would listen to all the events we wanted and add them to one big data model in the database. And each event would map to some fields in the model. And the fields would be exclusive to the event. So we wouldn't need to worry about some race conditions between them. We would just store data as it is. And later, we would make the control panel run queries on top of this database. And in this case, it was Elasticsearch because it worked well for the type of queries we wanted to run. And the nice part about this end result was that we actually achieved the architecture we wanted to have in the first place, right? So we had this control panel running a query on a big database. And the reading side, right, the side running queries didn't even realize that this data was built from events, which was interesting. And the writing side was also separate from the reading side, right? So we had this process of reading events and making up a model of them and storing in the database, which was the writing side, and then the reading side, which just fetched what there was in the big model. So remember this slide because it will become useful later. And a few other insights about this project. So testing was a challenge because we had tens of microservices that produce the events, right? And one of the rules we had about testing was that you shouldn't need the entire platform locally to test your service. So we wanted our test to be fast and independent, not break if another service breaks. So we wanted a way to test our queries without depending on other services in the company. And we ended up emulating them. So we built an event simulator that would run locally with next to the tests, and we would use events from the production anonymized that would be fed to the database. So thanks to this, we didn't have to contact the services directly. We didn't have to run them next to our service. We could just use the fake events. And the other challenge was embracing eventual consistency. Because of the nature of events, the data on the dashboard would be usually out of sync with the state of the system. Usually a couple of seconds maybe, or shorter, but it could happen. So it's not something we can solve technically, right? But it's something we need to talk about with whoever is using the dashboard. And in our case, what helped was live updates using server-sent events. So at least the operators didn't have to, mash the refresh button, because the website would update every time a new event came in. So the lesson learned here is that, in the first project, I learned that having separate write and read models is fine. But here, the idea is a bit further, right? So we have this one big read model and a set of smaller write models, which suggests that maybe it's also possible to have like a couple of read models and one big write model or any other configuration. So it's not only about this split into two, but this any number of models that make sense for the project. And the other insight is, when you talk about read models, it can mean two things in different contexts. So in the first project, it was just a response struct, which was simply a different projection from the data we kept in the same database. But here, it was an actual data model we stored in the database, like a separate model from the data we used to fed to it. So it is a big difference when you talk about with your colleagues in the team, because if you say something like, we need to use a read model, you need to be more explicit, right? If you want to store it, or is it just a projection from the API? Right. So moving on to the third project. It was a project in the e-commerce domain, so you can think like online shop, but more custom than Shopify. But it's basically the same idea. And the business started with the lean startup approach. So the founder had an idea for a business, right? But they didn't know if it makes sense. So they hired a freelancer to build an MVP for them. And it would be a trivial web application that just would help them decide if this idea makes sense or not. And they would see if this MVP can make money, right? Which turned out to be true. And the company became a startup thanks to this initial code. And it was, again, this trivial architecture of front-end client, backend Go server, and a database. But in this case, it was SQL. The only issue was, the MVP code, which the nice part was it worked, right? It helped the company make money. The customers were coming in. The sales team was happy to sell features that didn't exist yet. But if you work with any kind of legacy software, you know how it usually looks like, right? So no tests, some tech debt because there was rapid development, and any changes are risky because you don't know what can break. You've probably been there before, so do you know what's the solution to this? So here's a hint. It starts with re. So first there's rewrite, right? So you think, yes. So we know how it works, right? The product is working. All we need to do is just rewrite it in better tech stack and from scratch. Add tests. It will be just better overall and modern and so on. So it makes sense, but then you consider, yeah, but we need to stop development for like 6 months to make it done. The product will just stay in place, and we already sold customers features that are not there yet. So it doesn't seem that nice after all. So the second one is refactor, right? Because then you think, like, come on, it's just code. How hard can it be, right? We'll just take this old legacy software and gradually make it better. Just add tests and introduce some cool approaches and so on. But then you pick up a task that you think will take 2 days and it takes 2 weeks. And you're like, yeah, I'm not working with this shit anymore. So there's also the third way, which is rethink your life with. But assuming you stay, you basically need to do this, right? You have this old code that goes nowhere. Like, it's clear the company can't use it anymore. And there's the new code that doesn't exist yet, but you somehow need to make it there. So it should basically do the same as the old one, but have no issues, right? And enable us to have even more customers and make even more money. All you need to do is migrate, which sounds simple, right? Just move from the old to the new one. The issue is it's pretty much like fixing a plate midair, right? So you can just stop the company for a year and rewrite it. You have to do something more clever. So we didn't know which approach to take, really. So we decided to start small, right? We would do small experiments in some areas and just see what works. Maybe you continue or drop it, but at least it won't take 6 months to do it. And it helped that the old code was kind of modular. And one of the biggest pain points was the product area. So it was basically like product inventory in e-commerce application. And almost every other module depended on it some way. And it was the biggest pain point when introducing new features because the data model was quite limited and we couldn't just do what we wanted without improving it. So we started looking at the whiteboard, how it works. So we had this database and the products table and clients who would put the products in the basket, place an order, buy it, right? On one side. And on the other side, we would have administrators or the operations team who use the internal tooling platform to manage those products. So like update descriptions, add new products, change prices, and so on. And this is when the pattern recognition kicked in for me, because it seems similar, right? Because if you think about it, it's this split. So we have the left side, which is the reading side, because customers make no writing changes to the products. The only writes come from the right side, the operations team. And this gave us an idea how to move forward. So we would introduce a new set of tables that were more extendable, better suited for new features. And they would become the write model. And we would create a 2.0 version of the internal platform for administrating them, while the MVP code would still use the products, the old products table, the read model. And every time something changed in the products table, the new one, we would synchronize the changes. And the best part of this idea was that we didn't have to touch the old code at all to make this change, because similarly to what happened in the second project, as far as the MVP was concerned, it used the same SQL models, or the same tables. It didn't care that they were fed by some other process. And sometime in the future, when it made sense, we could create this 2.0 for clients as well, the user-facing side that would use the new models. But thanks to this initial split, the migration would be much easier in the first place, because it was already complex enough. But thanks to this, we didn't have to consider how the MVP can break. We just had to consider the mapping we had to do, and we did it in a synchronous way. So every time the models changed, we just updated the old tables as well. We could also pick a asynchronous approach, right? So we could have the new version publish an event every time something changed, and then ingest it in the MVP and update the models. But we decided we didn't really need this more complexity, and synchronous was good enough. So the big lesson learned here for me was that, how working with a similar project before helped me very quickly recognize this setting, right? So having one side just doing the reads and the second doing the writes, which is something I saw with the control panel project. So where is CQRS in all this, right? I didn't mention it even once. So I guess we can now go back to some definitions, because sometimes they are useful in the right context. So it starts with command query separation, CQS, which is an old idea from object-oriented programming, right? And it says something like, for every method in an object or in a struct in Go, split your methods in two parts, in two kinds. And the first one is a command that modifies the object, has side effects, but returns no data. And the other is query, which returns data but has no side effects. So basically, reading data should not modify the system. That's the idea. And CQRS is this idea taken on my architectural level. So Greg Young says about it that it is the creation of two objects where there was previously only one. And the objects he has in mind is this one, right? So in your code, this can be called service, controller, or whatever else, handler maybe. But basically, there is this place where you define all the actions that someone can make in your system or on an entity. So CQRS says you take this thing and split it into two, right? So you have two interfaces now. You have commands for things that modify the state, and you have queries for things that are read-only. And Greg says that it forces a break of the mental retardation, that because the two use the same data, they should also use the same data model. And this is the part that resonates with me, because it means the queries can now use a different struct in the response than the commands used for changing the state, which is really a trivial change if you think about it, right? You just take this interface and split it into two. But what I think it helps you do is change your mental model from thinking of this single entity as a source of truth for everything to having a separate model for writing and reading. Because in this context, having a user used in commands and user response using queries looks kind of okay, right? Like seems fine. But if we had this single service interface and suddenly used user response in the queries, it might look a bit weird, right? Like you could see like a PR command. Why are you suddenly using a different object in those methods? But if you do this simple change, suddenly, yeah, it seems natural, right? Why not? And there's some bonus things that come with CQRS that you might have heard about before, like polyglot persistence or eventual consistency or even sourcing. And yeah, it's true that CQRS makes it easier to work with them. But in the essence, it's just this basic change in your interfaces. So my take is maybe a bit controversial, but yeah, I think the split of services is not really the end goal, right? The end goal is to change your mental model. So you no longer think of having a single entity as the source of truth, but you start seeing use cases in different places in your system where a different data model makes sense. And this is from me. Thank you.